Good morning. We all know each other. Welcome to Miami once again to this exceptional occasion, the celebration of Donald Spencer's to his contributions to mathematics. So we have a full and very intense program for you. The announcements will come along, and more and more people get just on their ways, and so will be arriving. So the announcements will be repeated. So, but we are very happy here to celebrate all the achievements that Donald Spencer has really projected for us. Of course, one of the best ones, one of his best contributions to mathematics sits right here, that's Philip Griffiths, but there are many others that he has actually created for us, and that's what we'll be discussing this week. So let me start with introducing one of the main supporters of IMSA through the years, the president of Mexican Academy of Sciences, Pepe Seade.
Thanks a lot, Junior. Thanks a lot, Professor Griffiths, for the invitation. I'm really very happy, very honored to be here. So I'm going to be talking about mostly work with Ángel Cano from Mexico and two colleagues, Barrera and Navarrete. Let me start from the history. Some earlier research that I started with Alberto Verjovsky in the late 1990s. And we can think of it as being Kleinian groups in several complex variables. So let me start from the bottom, very quickly. So a Kleinian group is, by definition, a discrete group of Morris transformations. It was introduced by Poincaré at the end of the 19th century. And well, we know that the Morris group is isomorphic to PSL2C. It's also the conformal group in S2. And it's also the isometries of three-dimensional categoric space. So a group like this can be regarded as a projective group, as a conformal group, as a group of isometries. So there is great richness and many viewpoints to study them. And in the first decades, the interest was more in the subject of automorphic functions and the uniformization theorem, and differential equations. Till the 1950s, more or less, and Alfors and a little later Bears reshaped the field, bringing a more dynamical viewpoint. And then there was also important work by William Krah, Bardeen, later Thorsten and Sullivan reshaped it again, bringing a more dynamical viewpoint in connection with three manifolds. And well, Bill Holman made very important contributions to the representation space perspective, and many others which I'm not mentioning. And then at the same time, more or less in the late 70s, 1970s, there was a lot of work reviving the theory of iteration theory, which was begun by Julia and Fatou in the 1920s, 1930s. But then in the 70s, the theory was revived, and there was a lot of work by Rodin and Howard. And then in 82 there was Dennis Sullivan's dictionary, which established a framework to think on how ideas and results of iteration theory in one complex variable could be translated and vice versa into ideas and results in Kleinian groups. So on the one hand, you have one rational map of degree more than two or more. On the other hand, you have finitely many Mobius transformations, so rational maps of degree 1. And the two theories were different with many parallelisms. And then Sullivan and all this work by Dobie and Robert and all the work in hyperbolic geometry somehow inspired a boom in iteration theory. And in the early 1990s, there were very striking results in iteration theory by Bedford Smiley, Bernay Siboni, and many others. And then Alberto was in Mexico, and we were just learning about this work in iteration theory. And then we started thinking, well, you have one dimension, you have Sullivan dictionary, Kleinian groups, iteration theory. While you have iteration theory in several complex variables, what there should be in the other side of the dictionary. And then we can, with this idea of working with discrete groups of projective transformations in complex space, in complex projective space. So we define the concept of a complex Kleinian group, which we meant by that a discrete subgroup of PSL n plus 1c, which acts on the projective space with a non-empty open space of proper discontinuity. And well, this idea, this concept includes several important families, as for instance, the holomorphic isometries in the complex hyperbolic n space, a subject I started studying in the Waldemar book. Generally, reutilizations of the Lorentz groups. It includes also the affine groups, and it includes the real hyperbolic, isometries of real hyperbolic space, which are embedded in a natural way, but they can also be embedded in many other different ways. So this is a concept that somehow unifies several interesting areas of mathematics. Then Alberto and myself studied with more care some very interesting families. One was the groups that we constructed via twistor theory. Just a few words to recall that if you have to start the four-dimensional sphere, then its twistor space is CP3, and you have a natural vibration, the twistor vibration, with fiber CP1. And the idea, the starting point of twistor theory is that the conformal geometry of S4 interplays with the holomorphic, with the complex geometry of the twistor space, CP3. And then we prove that the projection is maps Penrose and his team, they knew that the group of conformal automorphisms has a canonical lift to holomorphic automorphisms of CP3. And then we show that that group, if you look at the action on the fibers, it was by isometries on the fibers, which are CP1. And then that allowed us to translate the conformal dynamics in S4 into holomorphic dynamics in CP3. And we proved interesting things, and they generalized to higher dimensional projective spaces. Then we also looked at complex Schottky groups. Let me recall that the Schottky groups, the classical, not so classical, where if you have a circle on S2, this gives you an inversion. And if you have a joint family of circles, each circle serves like a mirror, gives you a transformation that maps the outside into the inside and the inside outside. And then if you have these finitely many disjoint circles, you can make a pinball dynamics looking at taking these inversions as generators. And you have fascinating dynamics. So we look at the same idea in CP2n plus 1. And then we saw that if you have any projective space of dimension n, you take a thin tubular neighborhood that plays this role of a mirror. The neighborhood splits the projective space in two halves, and you have holomorphisms interchanging the inside with the outside. And if you have finitely many of these, you can make this kind of ping-pong dynamics again. And we define complex Schottky groups. We study what we call the limit set, which is that you take one of these lines, one of these spaces, and you look at where it accumulates. We call that the limit set. We show that the action on the complement was properly discontinuous, that you have a compact orbifold closure, and we study the topology and the dynamics and the limit set, the deformation spaces, and so on. And somehow that was the starting of a line of research that we have continued in Mexico. In the early 20s, we started forming a school in Mexico in the subject, and Ángel Cano and Navarrete, who I'm not really talking about the war, and another one, they were our students. Now Ángel is my colleague, and I would say my teacher. And somehow the aim is to lay down the foundations of the theory of complex Kleinian groups. So with Verjovsky, we realized that it was a very interesting subject. We constructed very interesting examples. And now we've been trying for these 2 decades to study them systematically. We're starting from the first non-known case. The first known case is CP1, the classical case, which is very interesting. Still many things to be known, and many things already known. So next dimension is CP2. And so we've been studying all dimensions, we're mostly focusing on CP2. And I'm going to concentrate on CP2. So I'm going to work from now, our work by Barrera, Ángel Cano, Navarrete, mostly, and myself, and also contribution by some other people in Mexico. So the first point is what's the limit set? So classically, we know that you take a point in the sphere, you make the group act, and you look at the set of accumulation points, and that's the limit set. And that's well defined from many, whatever viewpoint that you have, it works. And the reason, one of the main reasons why everything works beautifully is because in Kleinian groups you have something which is called the convergence property, which means that if you have any sequence of transformations in the group that converges to a limit, well, it has a subsequent subsequence which converges, and in the limit it converges to a map which has a very beautiful property. You have 2 points A and B, and if you remove A, everything goes to B. Or if you remove B, everything goes to A. So that's the convergence property, and that's beautiful. That allows you to do many beautiful things. In CP2, you don't have that property. So you have to go around it in one way or another. Okay, so you have these definitions of limit set. I will come to this in a moment. They are very beautiful. They are related. Now we understand them, and I will explain this. So I start with the Poincaré's limit set. You take a discrete subgroup transformations, and then you look at 3 sets. First is that the closure of the points with infinite isotropy. You remove that, you look at the complement, and you look at points here, and you look at the closure of points here. And now you remove these 2, and you look at compact sets in the complement, and you look at the accumulation points of the compact sets. Now you take the 3 of them, and that's the Poincaré limit set. It's defined in a much more general setting. It's very general. Somehow it doesn't look like a very natural definition, but it has one big advantage, that is that you have for granted that the action on the complement is properly discontinuous. And we will see that, at least in the main, for complex projective space of dimension 2, it is a very interesting concept. It's always closed, it's invariant. And one of its interesting properties, it has many properties. One interesting property for us, which will be useful, is that it allows a classification of the elements, it allows a geometric classification of the elements in PSL N+1C. Let me recall, to play this quickly, let me recall the classical. So for knowledge transformations, we know that they are all of 3 types, which are elliptic, parabolic, and loxodromic. And one way to define them is the Jordan form of any element here is one of these two types. If it is diagonalizable, it's like this, where for some complex number, non-zero complex number. If it's not diagonalizable, it's like this. The elements that correspond to this are the parabolic elements, and regarded in the external complex plane, they are just translations. Regarded like this, if lambda has norm1, they are rotations, and those are the elliptic elements, and otherwise, they are the loxodromic elements. Okay? And dynamically, geometrically, this can be regarded like this. In the complex line, an elliptic element is a rotation. So if it is by a rational angle, it's a final group, and the limit set is empty. If it's an irrational rotation, the limit set is all of CP1. A parabolic element, the limit set is 1 point. The loxodromic case, the limit set is 2 points. Okay? This generalizes beautifully to all dimensions in a most natural way. You have an element in PSL n plus 1c. You lift them to SL n plus 1. And an element is elliptic if the lifting is diagonalizable with eigenvalues of norm 1. It is parabolic if it has a lift with eigenvalues which is non-diagonalizable with eigenvalues of norm 1. And it is loxodromic in all other cases. Okay? That's just a definition. So what? It has a very beautiful interpretation. So let me say that for elements in PU n plus 1, it coincides with the definition. I forgot the second step. No, in the first case for elliptic elements, you can characterize them by saying that the Poincaré limit set is either empty or the whole projective space. So exactly like in dimension 1. For parabolic elements, the limit set is one proper projective subspace. And for loxodromic elements, the limit set is two proper projective subspaces. So in the case of CP1, we are talking about 1 point or 2 points. And in the second year, you already mentioned that among the loxodromic elements, there's a class which is especially interesting, which is what we call strongly loxodromic. And are those which correspond to matrices of this form, where the eigenvalues have different norms. Those are what we call strongly loxodromic. They play a very important role. In this case, you have one eigenvalue of maximal norm and multiplicity 1, and the inverse also has one eigenvalue of maximal norm and multiplicity 1. So that's what in the theory of constant diverge are called by proximal elements, and that's very important for us. So just to close this part, let me mention some properties, important properties of the Poincaré limit set. And maybe, let me do it in comparison with dimension 1. Dimension 1, we know that the limit set has 1, 2, or infinitely many points. Here, it has 1, 2, or 3 lines, or else infinitely many lines. The second property makes no sense here. And in CP2, you can ask how many lines you have in regular position. Okay? And you can prove that it has 1, 2, 3, or 4 lines in general position, or infinitely many. Just a remark here, if you have 4 lines in general position, in particular, you have 4 lines. So it means that you have already infinitely many lines, or at most 4 in general position. I'll come more detail to that. Then the region of discontinuity, which is the complement of the limit set, in this case, classically it has 1, 2, or infinitely many components. Here we have examples with 1, 2, 3, 4, or infinitely many components, but we do not know these are all possibilities. So we don't know if there can be 5 components or 7 components. I don't know. Generically, the limit set is the closure of the fixed points of loxodromic elements. Classically. Here is the closure of the attracting lines of loxodromic elements. Now, it contains, just a remark is, in general, it consists of lines. But it can have one isolated point. But if it has one isolated point, then the limit set is 1 point and 1 line. And we have characterized those groups. One more thing is, classically, the group is said to be elementary. The limit set has finite cardinality. Now we say that the limit set is elementary. If the Poincaré limit set has finitely many lines in general position. And well, let me say that in one dimension, the elementary groups somehow are not especially interesting. Here, they do play an important role. There are many, many classes. Let me just mention something. The elementary groups, let me say that there are 7 types of elementary groups which are purely parabolic. These are fundamental groups of the complex toroid. Some groups which are algebraically dual to this, extensions of the fundamental groups of innovative surfaces, collider groups, and some other groups. See? And in all these cases, when you have parabolic elements, the limit set consists of either one line or a cone of lines parameterized by RT1 with one vertex in common. So you have two lines in a general position at most, but you have infinitely many lines. And then you have 7 more classes of elementary groups which contain loxotronic elements. And this gives you limit set one line and a point, 2 lines, a pencil of lines with a common vertex, or exactly 3 lines, or a pencil of lines of the P1 with one common vertex and one more non-concurrent line, or or 4 lines in general position. Okay. Now, just let me say one more property, very important thing in differential geometry, of Kobayashi and Kochiyai. If you have a compact surface, with a projective structure, then it is known that M is either complex hyperbolic or complex affine. And we proved that if you have a group which acts on CP2 with so there's an open invariant set with compact quotient, then the group is either complex projective or virtually complex affine. And the open set is the Kulkarni open complement of the Kulkarni limit set. And then we classify the open set that can appear in this way, the groups, and the quotients or rifts. Now, let me move to the second type of Myers limit set. This is much related with what I call, well, I mentioned the convergence property. So for Kleinian groups, you have the convergence property I mentioned, that every sequence converges to a sequence, so that if you have, you can remove 1 point, 2 points. If you remove 1 point in the spin in CP1, everything is mapped to one other point, and vice versa. You don't have that in CP2 or in CPN. So we define what we call pseudo-projective transformations. What's that? That means that a projective transform, a projective automorphism, you look at Cn plus 1, you have an automorphism there, and then you projectivize it. Now, you can look at a linear transformation in CPN, which has kernel, non-trivial kernel. You remove the kernel, and you can projectivize it. That's what we call pseudo-projective transformations. Okay? It gives you a compact space, and it gives you a compactification of PSL plus 1C. And so in the case of CP2, it's very beautiful, because then what you have is that every sequence in your group has a subsequence which converges to something with the limit, so that either you remove one line and everything is converged to a point, or you remove 1 point and everything is taken to a line. So it's a very, very, very beautiful compactification. And using that, and we can define the pseudo-projective boundary of a group, which is all the limits of the group inside this space. We call that the pseudo-projective boundary of the group. And you can look at all limits of the given group. And you can look at the kernels of the corresponding sequences. That is the Myers limit set of the group. And it's a very interesting set because its complement, you can prove its complement is the equicontinuous set of the group. Okay, and then we prove that, well, this is the complement of the equicontinuity region. It contains always the Kulkarni limit set. And if the Kulkarni limit set has at least 3 lines in general position, you need 2 of them coincide. Now we're going to do a third concept of the limit set. This is the concept this is rooted in the theory of Furstenberg boundary maps. And we look at an automorphism in Cn plus 1, you say that it is proximal, it has an eigenvalue that dominates all the others, and it has multiplicity 1. And a dominant, an eigenvector of this eigenvalue is called a dominant eigenvector. And then you pass to the quotient, and you have a proximal element. An element is proximal if it has a lift which is proximal, and so on. So if you have a proximal element, A dominant eigenvector gives you a fixed point in projective space, which is attractive. Okay, so proximal elements have a unique attracting point in projective space, and one can show that in PSL3C every proximal element is loxodronic, and every loxodronic element either it is proximal or its inverse is proximal. Okay, so proximal elements are very close to loxodronic elements, and by proximal means that the element is proximal and its inverse is proximal. Those correspond to the strongly loxodronic elements that I mentioned. Then the consecutive Arch limit set is by definition the closure of the attracting fixed points of proximal elements, which is the same, the closure of attracting fixed points of loxodronic elements. One more definition of them is that a group is said to be strongly reducible if its action on CP2 does not have points or lines with finite orbit. Okay? And then they prove that if you have a strongly reducible group, then this set is non-empty, and it is the unique minimal set for the action on CP2. This is more, the theorem is more general. I'm focusing in our case. Okay. So the next lemma is if you have a group which is strongly reducible, then its Poincaré limit set is a union of infinitely many lines in general position. Just let me give you the idea of the proof is very simple, just because it uses the things I mentioned. So if the limit set has only 1, 2, 3, or 4 lines in general position, if it has 1, 2, or 3 lines, then the limit set is invariant, then the group is living invariant, an algebraic set, then is by definition is not strongly irreducible. So it cannot be. If it has infinitely many lines, or only 2 in general position, then as I said, it is a pencil, it is something like this. Here you have an RT1, and you have all the lines passing by 1 point. Then this point is a fixed point. Then the group is not strongly reducible. If you have 3 lines, you can show that the limit set is something. If you have infinitely many lines, but only 3 in general position, then the limit set is something like this and 1 more line. But if there is an invariant set, then again the point and the line are invariant sets and is not strongly reducible. And if you have 4 lines in general position, then we know that you have 2 pencils like this, which are transversal. Then the 2 points give you an invariant set and is not strongly reducible. Okay. So this is very easy lemma, thanks to the fact that we know all the previous classification of the elementary groups. Now, just one more remark. If you have a projective group, it also acts canonically on the projective dual. This is the space made out. Points here, lines here correspond to points here. So the action of the group here also acts on the dual. I mean that you have the consecutive value limit set for the dual action. Okay? Now, if the group is strongly irreducible, it's also this set is also the minimal set for the action in the dual space. And then we have a very beautiful classification. If the group is strongly reducible, then the Poincaré limit set coincides with the Marbury limit set, and it's a union of infinitely many lines. This I have already mentioned before. Now, in that case, this set is the closure of the attracting invariant lines of loxodronic elements. Attracting invariant lines. This line is the closure of the attracting fixed points of loxodronic elements. So loxodronic elements may have either one line, the limit set is for one loxodronic element consists of either 2 lines, one is repelling and the other is attracting, and for the inverse, one is the converse, or 1 line and 1 point. Okay? Then inside here you have 1 attracting point in each line. So for consecutive Arch, you look at the attracting points and you look at the closure. For Poincaré, you look at the attracting lines and you look at the closure. And one more very interesting thing, you look at the Kulkarni limit set here, and then you map it into here by duality, and what you get is the consecutive limit set of the dual action. And vice versa. You look at the consecutive limit set of the dual action here, and you take the inverse image of the set, and what you get is the Kulkarni limit set. Okay? So these all are really beautifully related, different concepts coming from different areas, and they all fit together very, very nicely. Now, we've been speaking about the limit set. Now let me talk about the complement of the limit set. So in the classical case, we know that the complement is equal continuity region, and they have many beautiful properties. Here are those two. If you have a group which is strongly reducible, then every connected space here is a complete Kobayashi hyperbolic space, and it is hyperbolically embedded in projective space. Hyperbolically embedded, let me remind. Kobayashi, I think you all know, being a Kobayashi space means that the Kobayashi pseudometric is symmetric. Complete, that it is complete as a metric space. Hyperbolically embedded means that approaching the boundary inside Pn requires infinite Kobayashi distance. So if you have any sequence going towards the boundary, the length tends to infinity. And tout means that every converging sequence of holomorphic maps from the list into the set either converges uniformly in compact sets of a holomorphic map, or it eventually escapes away from all these compact sets. Okay. And it is known from complex analysis that hyperbolically embedded in this setting, hyperbolically embedded implies time, and this implies time, and these two together implies a domain of holomorphy. So you have all these properties in this setting. Just a sketch of the proof, we know that it has infinitely many lines. So take a component here and take a Cauchy sequence and suppose to prove completeness. Suppose it doesn't converge in your space. Then it converges to some point in the boundary. Well, the boundary is formed by lines. So suppose it's converging to some point X, take the line here, a line here which passes through X. Okay? Now pick 4 more other lines. You have infinitely many, you choose 4. Then you have, let me call F5 the complement of those 5 lines. By Green's theorem, we know that F5 is complete and hyperbolically embedded. Green's theorem tells you that if you have finitely many lines in CP, in this case, in CP2, at least 5, but finitely many, then the complement is Kobayashi hyperbolic and hyperbolically embedded. The problem here is that we have infinitely many, have too many, then you have to prove something. Okay, so then you have that this is complete and hyperbolically embedded. Then your Seade sequence here must converge, but you know it's converging to this point, which is in F. Okay, so that implies it actually converges also in F. Okay. Now let me come to the last object. Well, I will not go into detail. It's very, very deep theory. For classical Kleinian groups, well, we know the Patterson-Sullivan measure. It's a very, very important probability measure. It's fundamental in theory of Kleinian groups, and it has support in the limit set, and it's quasi-conformal under the group action. And it's in general, it's a Godic on the limit set, and it reflects how dense the limit set is at the meeting. Then Canary, Shang, and Senior in a recent article define a Patterson-Sullivan measure for actions of what they call transverse projective groups on the flux variety. I will explain this now. And this measure has support in a limit set that they define, which springs from a quint unit set defined for semi-simple groups. So let me explain this briefly. So just in our setting. This is more general. The result is much more general. Just let me restrict to my setting. So you have a discrete group here. If you look at the manifold of flux, this is one. In C3, this will be a point, line, two-dimensional spaces. When you projectivize, the full flag is just a point and a line containing the point. Okay? That is the flag you're looking at. Now, given an element here, related here, and you have the singular values. So this one is usually the direction in which it's more expanding and so on. Let U1 correspond to the point in which you have this singular value. So this gives you an attractive fixed point. Now you take a line which is given by this point and the second singular value. So you have a line that contains this point. So this gives you a canonical flag. Okay. So you look within your group, you look at this flag, and you look at the orbit under the group. And you look at the closure, and that is the quint limit set. Okay. And you define the group is transverse if all flags in the limit set are transverse. And this means if you are given two flags, they are transversal if the point in this one is not in this line, and the point in this line is not in this line. Okay. So two flags are transverse if this happens, and the group is transverse if all flags in the quint limit set are transverse. And then with this definition, they construct a Parkinson-Sullivan measure having all the properties, most of the properties of the Parkinson-Sullivan measure, and this has support in the quint limit set. Okay. Now, an observation is just an observation is that if you have transverse, if the quint limit set, if the group is transverse, then there's a natural projection from this variety into P2. There are actually two projections. Every flag can be projected to P, CP1, or to the dual space. And then because the flags are transverse, these two projections are automorphisms. Okay. So the Patterson-Sullivan measure you have on the flags can be just pushed to CP2 or CP2 as well. And then that gives you a Patterson-Sullivan measure in the projective space with support in the constant diverged limit set. Okay. And then we can now propose a Sullivan-type dictionary in dimension 2. The lexical objects are comparing on one side endomorphisms of CP2. Here you could put rational maps, but then there are many exceptions. Here we put finitely generated strongly reducible groups. You could put more general, but again, we have many exceptions. So to make it clean, I put these two hypotheses: endomorphisms and strongly reducible. Then we have the Julia set, one side which is closed, with the Poincaré limit set, its counterpart. This is non-empty connected, total invariant, total invariant. Its complement is the continuity region. Here is called the Fatou set. Here the complement is the continuity region. Okay. And now some similarities. You have the first Julia set, which is by definition the closure of the repulsive periodic points. Here you have the constantly vanishing set, which is the closure of the repulsive fixed points of those chronic elements. This is contained in the Julia set. In general, they are not equal, but they can be equal. This is contained in the Poincaré set, they can be equal. Here, as far as we know, there is nothing corresponding to this, but the Poincaré set is the closure of the repulsive invariant lines of those chronic elements. We don't know if there's something similar in this other scenario. Now, the Fatou set is coherent hyperbolic. The Poincaré region is coherent hyperbolic. This is complete. This is an open problem. This hyperbolic element is better, hyperbolic element better. So convex, tau, Stein, domain of holomorphism, let's see. The exceptional set here is a finite union of lines. Here, the exceptional set is a finite union of algebraic monoidal curves. Here you have an equilibrium measure, which is invariant with supporting differential set. Here, for transverse groups, you have the Patterson Sullivan measure, which is totally invariant and has support in the consequent value set.
Yes. I got lost. What is a domain of holomorphy? What is the option? I got lost.
Yes,
Is the complement or what is the object that is a domain of holomorphy?
Each component of the complement of the limit set. Okay. So since this is an honor of Spencer, let me talk about something about deformations. It's not the kind of deformations that we want to do. Everything I've said here so far has been for strongly irreducible groups. And then you say, what if you don't have a group which is not strongly irreducible? Then this theorem says, look at the free group of rank greater or equal to 2, and we think of it as being the homomorphisms of the free group. And so sorry, we identify the homomorphism of the group into PSL3C with PSL3C to the R. That's around. Okay? Then we can give it the Zariski topology, it makes sense, and define this set to be the set of all representations of this free group into PSL3C, such that the image is a Kleinian group. This means discrete with non-empty regional discontinuity, and is not a virtually cyclic group. Okay. And look here at the subset of all those, such that the representation is strongly irreducible. Okay. Then this group, this set decides events in this set. Okay. As a corollary, we get that in the Zariski topology, every complex Kleinian group which is not virtually cyclic can be approximated or deformed to a group which is strongly irreducible. Okay? So if you have one which is not strongly irreducible, you perturb it slightly, and now you have a strongly irreducible. And the idea of the proof is more or less simple. It uses a concept introduced by Concept Large, which is Schottky type groups. I said before what is a Schottky group here. I mentioned the Schottky groups that Alberto and I defined. In CP2, you cannot have something like that. You cannot construct disjoint two-line neighborhoods or something. Just because in CP2 you have two lines they intersect, so you cannot have disjoint mirrors. Then they define something which is Schottky type. They're not Schottky, but they behave like Schottky, and the definition is very beautiful. You start by considering what they call a finite symmetric set. That means that whenever you have an element here, you have also the inverse in that set. Okay. So that is going to be your generating set. Now, fix a point and consider pairwise disjoint compact subsets which satisfy two conditions. First is that for every element here, first that the point is not in the union of all of them, and for each element in the group, the image of the point is in the corresponding set. Okay, so it's a point that is outside all the sets, but by each of the maps is mapped inside. And secondly, that each set is mapped to the interior of the other one. They are pairs, and each of these maps takes one of the sets to the interior of the other one. Then the group is called Schottky type. And then using this, we do the result. Here's the following. The first step is that we consider here, you look at the generators of your group. Okay? And now, the strongly hyperbolic elements here are dense. So you look at the generators and you perturb slightly so that you have two strongly hyperbolic elements with no fixed point in common and with no line in common, not invariant line in common. You can always do it. Okay. Then under these conditions, constant division implied that some power of the perturbator group is Schottky type, some power. Then you look at this power on the projective dual space. It's strongly reducing, and you have a certain limit set, which is a Cantor set. And then being a Cantor set which is not dense in CP2, if you look at the inverse image, you have a family of lines in CP2, and you have infinitely many lines here. And then you use what is called the topological Pitts alternative, that gives you this group is a least dense in here. And then that's essentially it. And that's it. Thank you.